Hi, this is a video on pressure sensors, and specifically we're going to start looking at mercury barometers. Before we get into the barometer itself, let's look at another application of mercury and force and pressure, and that's manometers. What a manometer is, it's an instrument that measures the difference in pressure. It has a U-shaped tube that's typically made of glass. In that tube is filled some fluid, and typically that is mercury. Both ends of the tube are open, so you can measure different pressures. One is typically open to atmospheric pressure, and the other one, the other side, is open to some pressure that you want to measure. Perhaps maybe it's the container that's filled with gas, some sort of gas or something like that. So what the manometer measures is differential pressure, the difference between these two pressure sources. And what results, if there is a difference in pressure, you'll have a difference in height in the mercury column on either side. We're going to derive an equation for a manometer, and that'll directly relate to our mercury barometers. We'll start out with a very basic definition. What is pressure? Pressure is a force per unit area. What kind of force? Well, if we go back to Newton's laws, you remember that a force is equal to mass times acceleration. In this case, the acceleration that we're looking at is the acceleration of gravity. It's pulling the mercury down. And the mass is, of course, the mass of the mercury. To figure out the mass of the mercury, we can't take the mercury out and weigh it. What we do instead is use volume and density to figure out the mass. If you remember, density is equal to mass divided by volume, or mass per unit volume. And we can rearrange that equation to get mass equals the volume times the density, and that would be the density of mercury. What we're looking at here now is not just absolute pressure, but difference in pressure, differential pressure. So we have to, in this equation, use a delta P. And the difference is the difference in pressure between the two pressure sources. That relates or causes a height difference in the mercury column. Perhaps the pressure on one side is greater than the other, so it pushes the mercury column up or down on one side and up on the other side. So this difference in height is related to a difference in pressure. We'll take that difference in pressure and put it into our equation for pressure. So we have delta P, the difference in pressure, is equal to delta F, the difference in force, divided by the area. The area here that we're talking about is the cross-sectional area of the manometer's tube. And you can see from the diagram that the cross-sectional area is the same. In other words, the diameter of the tube is the same everywhere. This shows you a little bit closer up what we're talking about. We're looking at the area of that circle. And the height is the height difference delta H. So in our equation, we have a difference in pressure is equal to a difference in force divided by area. Now we already came up with Newton's law that said force is equal to mass times acceleration. Well, if we look at it in terms of a difference in force, the difference in force between one side of the manometer and the other, the difference in force is a result of the difference in mass because of the height of the mercury. It's not a result of the difference in acceleration because, well, this is gravity. Gravity is, for the most part, constant for looking at this manometer. So our equation is now the change in force, the difference in force is equal to the difference in mass times gravity. And likewise, we came up with an equation for mass as it relates to density. Now it's the difference in mass. And that's a result in the difference in volume times the density. The density of mercury is constant throughout this tube, but there is a difference in volume. And specifically, we're looking at the difference in height times the area. So here is our equations that we have for the difference in mass is equal to the difference in volume times the density. Well, what is the difference in volume? The volume is, in this case, a volume of a cylinder, and the volume of a cylinder is the height times the area of the circle. So our equation here, the area is constant, but the height is difference. We have a difference in height. So the difference in volume is equal to the difference in height times the area. If we put that into our equation for mass, now instead of a difference in volume times density, we have a difference in height times area times density. We're going to use this in our equation for the difference in pressure. First off, to get to the difference in pressure, remember that pressure is a force per unit area. So we have to take our equation for force, which is the difference in mass times gravity, and now put in or substitute for the difference in mass the equation that we just came up with that related to the difference in volume. And that was the difference in mass is equal to the difference in height times the area times the density. When you combine these top two equations, this is what you get. The difference in force from one side to the other is a result of the difference in height of the mercury column times the area times the density times gravity. That's basically just mass times gravity. And now if you go one step further and include the difference in force in the pressure equation, remember pressure is equal to force per unit area, but we're looking at the difference in pressure and the difference in force. If we substitute the equation we have for the difference in force into this pressure equation, our new equation for the difference in pressure, as you see at the bottom, shows that it's the difference in height times the area times the density times the gravity divided by the area. It looks like the areas cancel out. So this is our calibration equation for a manometer. And what it shows that when you measure the difference in height, you can actually calculate the difference in pressure if you know what gravity is at your location, and also you know the density of the fluid that you're using in your manometer. This is the calibration equation. We can rearrange this equation to look at how the height of the mercury column changes with pressure. And if we do the math, the algebra, we come up with it's simply 1 over rho g. So what this is saying is you'll get a change in the height of this column, this fluids column, with a change in pressure. Basically, this is your sensitivity. How much something will change, how much your instrument will change as a result of what you're trying to measure, a change in what you're trying to measure. So this equation is showing that the sensitivity of a manometer depends upon the density of the fluid that you're using and gravity. Gravity, for the most part, is constant, so it really does depend a lot on the density of the fluid. If we take a manometer and seal one side, in other words, close it off, and leave the other side open to the atmosphere, we've just created a barometer. Now, to do this, we have to evacuate the other side that we sealed. In other words, we have to create a vacuum on that other side. So it's not measuring the pressure on that side in that closed little area. It's measuring strictly the pressure that's coming in through the other side, the open side. So this is our barometer. A barometer is basically an instrument that's used in measuring atmospheric pressure. And actually, you can use any fluid. For years and years, we've used mercury. That is the preferred fluid to use. And the reason for that is because mercury is so dense. But when barometers were first discovered, believe it or not, they used water. And water was a problem because it was not as dense as mercury. So let's talk a little bit about barometers, mercury barometers. There are different types of mercury barometers. First, we'll get through the definition of mercury barometer, and then we'll work our way into the different types of mercury barometers. So the definition of mercury barometer, it's a glass manometer that uses mercury in the column, and it's used to measure atmospheric pressure. A mercury barometer is a manometer that the reference pressure is 0 or just about 0. In other words, there's a vacuum at the sealed end of the manometer. The mercury barometer is not a U-shaped tube like the manometer was. Instead, they just use a glass column. Typically, the glass column is about a ½ inch in diameter. The column itself is usually about 30 inches or more, probably slightly more, maybe 32 or 33 inches. There's a mercury reservoir at the bottom, and the force of the atmospheric pressure, pushes the mercury column up to a height of about 30 inches. Hopefully, there is a vacuum at the very top of it, but sometimes there are mercury vapors as a result of the evaporation or vaporization of mercury. Usually that is a very small pressure, and that may need to be corrected depending upon the instrument. The advantages of a mercury barometer are that they make for a very compact barometer, one that you can actually put in a room. The reason is because the density of mercury is very high compared to, for example, the density of water. Density of water is about 1,000 kilograms per meter cubed, which is about 2,000 pounds or 2,200 pounds. Whereas the density of mercury is 13,595 kilograms per meter cubed, or about 27,000 pounds per meter cubed. That's a lot more mass. So it's much more dense. It's 13 times more dense than water. As a result, water barometers, if you made a barometer out of water, it would rise up to 33 feet. That would be difficult to put in a room. But mercury barometers, the height doesn't go up very high of the mercury column, only about 30 inches because of the density of mercury. One disadvantage of a mercury barometer is that it is not as sensitive as a water barometer. If the pressure changes 1 millibar, you're going to have a significantly bigger change in a water barometer than in a mercury barometer. We can actually calculate this. We'll look at a change of 1 millibar. We have to convert that to pascals. 1 millibar is equal to 100 pascals. And we'll rearrange our calibration equation for the manometer, or the mercury barometer in this case, so that we look at a change in height as a result of a change in pressure. So here is our equation. On top we have 1 millibar, which is equal to 100 pascals. In the bottom of the equation, we have gravity, which is 9.8 meters per second squared. And we also have density. And this is where we're going to vary the density and look at the change in the height of both a mercury and a water barometer. For the mercury, the density of mercury is 13,595 kilograms per meter cubed. And if we do this calculation, a change of 1 millibar results in a very small change in the height of the column, only 0.75 millimeters, almost just 1 centimeter. Whereas 1 millibar change for a water manometer or barometer will result in 10.2 millimeters of change, which is significantly more. The other advantages of a mercury barometer, the vapor pressure at the top in the evacuated chamber of the barometer is very small. water evaporates more easily and it would produce more pressure at the top, so we don't have a complete vacuum. But with mercury, it does not evaporate as easily, and as a result, it tends to be more of a vacuum at the top of the barometer. Another reason we use mercury barometers instead of water barometers is because mercury doesn't freeze. Well, it freezes at a much lower temperature. Water freezes at 0 degrees Celsius, so that means a water barometer would be totally inadequate in North Dakota. Also, mercury is relatively easy to clean or purify. It's quite stable, and also it doesn't cling to the walls of glass, so you get a nice convex meniscus, which is the top of the mercury. In other words, it's easier to read and interpolate. So that's a little bit about manometers and also mercury.